Welcome to Wireless Future. I'm Emil Björnsson, and as usual, I'm here with Eric Larsson. How are you today?
Good morning, Emil. I'm fine. How are you today?
I'm great. It's still bright in the mornings, even if it's the darkest time of the year here in Sweden.
Indeed.
So today I was planning that we should think about this quote that sometimes people are referring to by George Bock, saying that all models are wrong, but some are useful. I guess it's a statistician that have been looking into data analysis in general. But if we think now about our field and that we will cover this topic, then what is really a model within wireless communications?
Yeah, a model. So I think if we really seek a definition of the term, I mean, it would be something to the effect of a mathematical description of either a physical phenomenon or some other behavior or something that we observe in nature, right? I mean, it could be the physics itself, or it could be the behavior of a human or a user in a system, for example. But a mathematical representation, I think, of a physical phenomenon.
Okay, so that is a model. So these models that we have, are they exact or are they wrong? Or is there anything in between being exact and wrong?
Yeah, it's a good question. I mean, at some point, I mean, this becomes like more philosophy than science, perhaps even, right? But I mean, if we think of physics, I think it's reasonable to say that, well, Maxwell's equations, for example, they are exact as long as we aren't in a regime where relativistic or quantum effects play a role, right? And the same with Newton mechanics, that it's it's exact, or we can treat it as exact if we aren't moving too fast, such that relativistic effects play a role. In quantum mechanics, I'm not sure I know, or whether anyone really knows. I mean, or is a quantum mechanic description of the world exact or not? Again, I mean, at some point this might become more belief or philosophy than science. Now, in wireless comms, we tend to rely, I think, mostly on physical models that are rooted in the Maxwell equations. And from that perspective, I think it is a reasonable starting point to take to say that those equations are exact representations of reality for our purposes, right? Then, of course, in practice, we usually don't solve, or often don't solve, Maxwell's equations directly, but rather rely on various abstractions for them that, take the form of like path loss models and Rayleigh fading and so forth, right? Which are certainly not exact, but rather idealized ways of abstracting away a lot of difficulties and still ending up with something that captures to the first order what's really going on in the physics.
Yeah, I think this is what you said here is also important, that models can be modeling things in different detail, but sometimes we don't need all of these details in order to understand the world around us. I suppose I don't understand quantum mechanics at all, but I still feel that I have a good sense of the basic physical phenomena around me, so that I can abstract away some of those effects. So you were hinting a bit about the Maxwell equations, and that maybe one can use simplifications. So if we start more generally, what do we need models for when we are doing wireless research or building wireless systems?
Yeah, what we need models for? Almost everything, right? I mean, from algorithm design to planning networks to evaluating or at least predicting performance of systems and of algorithms, and this goes on all layers. I mean, on higher layers, then we need models for like how do users behave, how do they move around, maybe geographically, like mobility models and so forth, right? What is the contents of, say, data packets that are transmitted in a wireless network? How long are they, and how what do they contain, and how critical is the contents that they have as well. On the middle layer, I mean, we need models to describe arrival processes, for example, of traffic, the intermittent nature of packet arrivals, I think is just one example. And then on the physical layer, we need models for the actual wireless propagation and for the circuits, for the hardware. I mean, antennas and amplifiers and filters and all the electronics that go into our devices. Noise, of course, thermal noise. So the short answer, I think, is everywhere. And the long answer is just, the partial list of examples that I gave, right?
Yeah, no, I think if we study any textbook in wireless communications, and irrespectively if it's focusing on the physical layer or at some of the other layers that you were mentioning, I think it's a lot about presenting a model and then presenting algorithms that might be used to study or communicate given that type of model. And yes, do you have the feeling that we are needing more and more detailed or accurate model now over time, or is it the same models that we have been using all along when building wireless systems?
Yeah, in a way, I feel like, we're getting, if you look at the literature on wireless comms or communications in general, I think it's probably correct to say that, the amount of knowledge around modeling and the number of different models that are around that people use is just increasing over time. And that might be the consequence of a number of effects. One, of course, is that folks do modeling will want to be productive, right, and come up with new models and so forth. Another is that having sophisticated models can be genuinely useful, both for performance analysis and prediction and also for algorithm design. But I think there is an important thing here that we ought to point out and stress, and it is the fact that there is a huge distinction between relying on a model for algorithm design and using a model for performance prediction, right? There's nothing really, there's nothing really that implies that just because you're using a particular model when you design your algorithms that you should or even can use the same model when you later evaluate its performance. I think a good example is in the MIMO and massive MIMO literature and methodology that we both worked, let's say, a bit on. And where it's rather common in some literature to build algorithms that rely on assumptions on the small-scale fading. So, for example, much of the traditional literature assumed uncorrelated or independent Rayleigh fading, and more recent literature, where I think you have been one of the main contributors, Emil, rather relies on Rayleigh fading models where you have correlation among the antennas, a correlated Rayleigh fading, right? And I think the point here then is that now, one of the main selling points, in my view, of massive MIMO technology is that it functions without making prior assumptions on the propagation environment. At least in its canonical form, TDD, reciprocity, and all that, right? So, which implies that when you design algorithms, you want to make the minimum amount of prior assumptions on your propagation and design algorithms that are just completely agnostic to what's going on out there, right? And minimum assumptions mean to use prior densities that are have as much randomness as possible or as high entropy as possible. And then the independent Rayleigh fading is a great model because it essentially tells us that we know almost nothing about what the propagation environment looks like, right? And then later on, when you actually evaluate performance and make predictions like what is this going to perform like in a real network, then certainly plug something in there which is more realistic, be it correlated Rayleigh fading or be it some channel model from the cost standard or somewhere else, right? I mean, it makes perfect sense. But my point here is that there is a huge distinction between designing an algorithm that requires no prior knowledge, like massive MIMO with independent Rayleigh fading, and evaluating it under more realistic conditions or for more realistic models on one hand. And on the other hand, to design an algorithm that assumes that, look, we have correlated fading with some very specific correlation matrix, and of course we can do better, right? But then we have prior knowledge that the algorithm needs, and which we don't know. Number one, how will it acquire? And number two, how accurate is it? To reiterate the main message here, again, I mean, we got to distinguish between reliance on very specific models for the algorithm design on one hand, and the use of sophisticated models for performance prediction and evaluation on the other hand.
Yeah, I think you are pointing out a very important message here, and that it's easy to sort of, you design your algorithm, then you evaluate it on the same models given its characteristics there, and there is the risk that we sort of are then making some or conclusions based on it that can be a bit misleading. I mean, on one hand, if we design algorithms for IID Rayleigh fading for this good reason that you were describing, and then we apply them with IID Rayleigh fading, they might then, for example, this pilot contamination issue that we have been discussing a lot in previous episodes, probably is at its worst under IID Rayleigh fading. To some extent, it's like that. At the same time, if we are modeling the correlated Rayleigh fading and we have correlated Rayleigh fading, we get maybe the best case situation, and probably we are somewhere in between there in reality. So we shouldn't use that side information when we design the algorithm, but we should evaluate the algorithm we have on a model that might be more realistic.
Exactly, that's my point. I mean, it's a bit analog to testing on the training data, right?
Yeah.
we when we build algorithms, we would want them to be as robust as possible and rely on as little as possible of prior knowledge, which might not be accurately available in practice. And then once we have our algorithms, then, well, let's go ahead and evaluate them on the best available, in this case, then fading models, and see how they perform. No question. So, yes.
And what you're alluding to there also with the whole race of machine learning, there we have the danger that if we are not using real measurement of the reality, but we are using our best models that we used to use for simulations, and then we throw a machine learning algorithm on it, it might be able to invert simplifications that we were having in the models, or all the kinds of things that you weren't supposed to actually exploit when designing the algorithm. So
yes, that is a great point indeed, I think. And you could train a machine learning algorithm to perform extremely well on some specific model that you have trained it on, but then we really don't know how does it function in other scenarios and on other models, right? And as a matter of fact, all the models we use for the wireless physical layer are quite specific. Even correlated Rayleigh fading might seem like a fairly general model, but indeed it's not. I mean, for number one, it requires stationarity of the fading, and number two, it's still, Rayleigh with correlation, right? And you plug in a lot of information in this correlation matrices, and even if you model your environment with clusters of scattering objects and all that, well, is still just the first order approximation of the actual physics. And over-reliance on that in the algorithm design, I think, is a dangerous path to go.
Yeah, so let us then focus for a while on the physical layer and talk about some of the models we are having there. So a lot of the basic work that we are doing is this complex baseband representation, where we are describing passband signals that are continuous with sampled signals that we have in the complex baseband. Is this an accurate representation? Are there cases where we should question the use of it?
No, I think you can say with a clean conscience that these are exact representations. I mean, at some point this becomes also a little bit like more philosophy or even religion than science, right? I mean, for example, what is time?
Yeah.
The mathematical description of time that we use in physical models is a real number, right? What is a real number? Well, it's a limit point of a sequence of, you know, rationals. That's one construction at least, right? And what actually tells us that time is a real number? Well, we don't really know, right? But or we can't really say. But given that we accept that, then certainly the things that you mentioned here, like complex baseband representations of narrowband waveforms and so on, these are just mathematical facts, right? That result from, well, the axioms of integers combined with the assumption that physical time can be represented as a real number. And the amplitudes for that matter. I mean, when we speak of the amplitude of an electric or a magnetic field, then can we represent that as a real number? I mean, there's some sort of like modeling assumption behind that as well. But if we accept that, then I think we can say that all these like models for signals that we teach in like signals and system class, they are just mathematically exact.
Yeah, but when we are developing these models, we might be considering, we're transmitting for infinitely long time and we have a limited bandwidth. But then when we use them, we are transmitting a block of a finite length, and no signal can be both time and frequency limited, right? Is this an issue to care about?
Certainly. I mean, but that is treated rigorously in theory, right? It's just the way approximated the way, because we'd want to stay with reasonably simple mathematics. So, I mean, I think what you're after here is like, well, the sampling theorem, for that to hold, it's actually a statement of a limit, right? Where you need, like infinitely long signal in continuous time, and then only such a signal can be strictly band limited, of course. But it's not that we cannot treat finite duration signals rigorously. It's more that we don't want to do it because the mathematics becomes so complicated that it obscures things that are really important.
Yeah, and in the systems that we are actually building, our signals are reaching a little bit outside the supposed bandwidth, and we have masks to say how much they are allowed to do that. So we are sort of treating it. So then, given the complex baseband representation, what about signals of system theory? Do we have linear time invariant systems?
Yeah, I think it's, I mean, one thing at a time, right? So linearity, yes, insofar the phenomena that we work with can be described as solutions to the wave equation, which for the electromagnetic case is the Maxwell's equation or set of equations. These are linear differential equations. So if x solves the equation and y solves it, then x plus y also solves it, right? So for that reason we have linearity. There are phenomena that appear in circuits and so forth that are non-linear that we sometimes actually need to consider. But if we think of just like wave propagation, it's absolutely linear. Time invariance, well, not really, right? As we know, if you have a transmitter and a receiver and they move relative to one another, then we'll experience Doppler. And the system that describes transmitted signal in, received signal out is time variant by all means, but that can also be modeled. I mean, as a first order approximation of like getting rid of the difficulty with the time variance is that we say that, well, let's zoom in on the time axis and look at the short enough interval during which the system is substantially static, or no, rather substantially time invariant. And that's what we usually call a coherence block or coherence time in wireless. So certainly we approximate away a lot of things, often, not always, but fundamentally, I mean, wave propagation can be described via a linear time variant system, and then if we chop the time axis up into small enough chunks, then we can, again with a clean conscience, I mean, say that we have a linear time invariant system there, right? So that's what we do in much of the analysis.
Yeah. So let's then have this clean conscience. We can chop up time axis into piecewise constant, linear time invariant systems. Then we often are modeling the coefficients of these impulse responses that we have then using Rayleigh fading. But let's for the moment just focus on a single transmitter and a single receive antenna. Then why do we get Rayleigh fading? Is this really a good model, or is it just the normal distribution that is underneath there? It is the simplest type of model. Is it just for convenience, or is this really what we are seeing in reality?
No, I mean, you can justify it through various different arguments, right? I mean, one way justifying it is through the central limit theorem, that you have a superposition of independent paths and so forth. But you can also use more physical models like the Clark or the Jake's model, where you model a superposition more explicitly. And so I think the short answer is it's a fairly good model when you have like rich scattering or fluctuating target. Goes back all the way to the radar literature, actually quite far back in the last century. Obviously, it's not an exact thing, right? I mean, for one thing, the Rayleigh distribution has like unbounded support, so there's always a non-zero probability that you get any arbitrarily large value you pick. There's a non-zero probability that you'd get that amplitude, which is obviously unphysical. On the other hand, the tail goes exponentially fast to zero, so in practice that's nothing we ever need to worry about. Perhaps the important feature really of the Rayleigh distribution is that it has a lot of mass around the origin, and I think best way to see that is actually to look at the squared amplitude, which is exponential, right? And the exponential, we know it starts at 1 and then it goes like down, but it has a lot of mass around the origin. And in fact, as long as we use a small scale fading distribution that has this property, that has a substantial amount of mass around the origin, then we'll get very similar conclusions as if we had Rayleigh fading. So the assumption on Rayleigh per se isn't really critical. Almost anything else would work there as long as we have this mass near the origin. The advantage with the Rayleigh is that the Rayleigh is the magnitude of a complex, circularly symmetric complex Gaussian random number, right? And we know that Gaussian distributions are just awesome to work with for many reasons mathematically. So I think that's really the best even justification for the Rayleigh density as such.
Yeah, I ran a simulation for one of my lectures where I had like 6 propagation paths coming from the transmitter receiver. All of them were equally strong, but they were coming in with a random phase shift. And then the distribution that you get then is very close to a Rayleigh fading case.
So to the bare eye, you can't tell the difference, right?
Exactly. I mean, so as soon as you have like more than 5 paths, it seems to work fine. Then we also have this Rayleigh fading model that people are considering, which I suppose this is when we have one path that is dominating together from the other one. I mean, from a central limit theorem perspective, we want to have many random contributions that have roughly the same kind of distribution. And then if one of them is much stronger than the other one, it stands out still.
Yeah, absolutely. I mean, if you have a direct line of sight component and then on top of that you have Rayleigh scattering, then the Rayleigh model is extremely good, right? The only thing is one has to be a little careful, I think, that when we use these models for algorithm design, the question is then what does the algorithm know, right? If for Rayleigh fading, then it's like, well, the algorithm might know the standard deviation of the variance of the Rayleigh variable, which is, well, it might not be known perfectly in practice, but it isn't a big deal. I mean, if you design your algorithm and you plug in a number which is slightly different or wrong there, it doesn't make a huge difference. So it isn't a big deal. Now, if you work with the Rayleigh distribution, then you need the path gain for the line of sight component, including its phase. And that's more dangerous to plug in as prior knowledge in an algorithm, because that the phase of that the phase of that line of sight component will change potentially randomly and on the same time scale as the Rayleigh fluctuations do, right? I mean, you move half a wavelength and the thing is completely wrong. You move, well, if you move half a wavelength, even the sign changes, right? So, so you got to be very careful there what you consider known by your algorithm. And I think we're back a little bit at what we discussed earlier here in terms of like models that we use for algorithm design versus model that we use for performance evaluation later. So I mean, a safe approach here would be to, well, let's design the algorithm as if we had Rayleigh fading. And then we get our algorithm. And then once we have it, we can play with it and we can evaluate how well does it work now if we instead had Rayleigh fading. That's absolutely fine. But if we design the algorithm up front for Rayleigh fading, it might be that this algorithm either needs a genie that tells us the phase of the line of sight component, or it needs some kind of mechanism for tracking that, right? Which is like a whole different game to play. So with that caveat, certainly these are classical models that have been used for many decades and are easy to justify from basic physics and also fit rather well with like measurements, right? So
yeah, so I guess also if we will use the same algorithm all the time in our system, but then the users move around, and sometimes one model is good in one propagation environment and sometimes another is good, then we might not be able to change our algorithm. But it seems like the tails of this distribution still have some kind of important impact. I guess in the lower tail, how often we get really deep fades that are bad. I think in textbook you can see these bit array curves, and you have different slopes or different location of the curves depending if it's Rayleigh fading or Rayleigh.
Yeah, but we gotta be careful with the tails, right? I mean, fortunately, for all reasonable models that I know of, at least the tail dies off exponentially fast to zero. So, which means that you just go a couple of sigmas out and it's zero to any practical practical significance. And there might be something to keep in mind when you say, like, I think you said that, well, there's a chance to get really high values, right? And there's even a whole category of algorithms that rely on exploiting multi-user diversity. It was like popular like 20 years ago to do research on and looking at like, well, you got these users out there and you kind of try to ride on the peaks and pick the one that has the best fading at the moment. And when you do that, it's like you take the maximum of a bunch of Rayleigh distributed variables, and then you're suddenly operating at the tail of the distribution where the model hasn't been really tested and verified by much of measurements, and where at some point it just becomes unphysical, right? So you got to be a little careful, I think, when arguing, when using the model too far away from the origin, let's say.
Yeah, no, I think you're pointing also here at the more general thing that a model might be good for what it was originally designed for, but then when we start to study its asymptotics, I mean, it makes sense that if you have multiple users, some of them will have a good channel, some of them will have a bad channel. So there is some kind of multi-use diversity. If you pick people when they have their peak values, then you should be able to do better. But that doesn't mean that you can study the asymptotics as was done in defining what is called the multi-user diversity gain, where you say, oh, when the number of users go to infinity and we magically knows all the channel realizations, then we can pick the best one and that value goes to infinity as well.
Yeah, asymptotics is always dangerous.
Okay, so let's move on a little bit. What about noise? We are often modeling noise as being just an independent, complex Gaussian random variable. Is that a reasonable model?
Yeah, I think much of the time. I mean, if we speak of thermal noise, then mainly, I suppose, here, then I think Gaussianity is an extremely good assumption. Then saying that it's uncorrelated, we got to be a little careful. I mean, it might be like reasonably white over frequency in many cases, but it's also common to assume, for example, in MIMO systems analysis, that the noise is uncorrelated among the antennas, right? We got to be a little careful though, because effects like mutual coupling can play in, for example, and depending on where the main noise sources are in the electronics, then coupling can make the noise correlated. So, but I mean, so this is first order of approximation. It's pretty reasonable to say that it's independent, but we should be aware that this is not an exact thing.
No, and you were maybe purposely not mentioning time there as well, because I think in addition to the thermal noise, there's also impulse noise sources, whether it's interference or something else that are appearing.
Yeah, but interference isn't really, well, what is noise and what is interference?
Yeah, exactly. That was what I was thinking.
I like to think of noise as really thermal noise. And interference stemming from like other man-made sources. It could be other radio transmitters, it could be other equipment that just interferes, right? I mean, it could be something, like a welding machine or something that generates impulsive and spiky. Interference, I think, would really be or electromagnetic interference, I think, would be the proper term here, although we treat it as, air quotes, noise when dealing with it mathematically often. But we got to be clear here, what do we mean by noise? Do we mean only thermal noise, or do we also mean other things, right?
Yeah, no, I was thinking about often in real system we use, I guess it's called interleaving, where we take our bits and we scramble them a bit and we send them not in the intended order, and then we mix it back again. Is this to sort of make it look more independent over time and frequency, or?
Yeah, certainly. I mean, but we got to again distinguish between noise on the physical layer that enters into our continuous time models for signals, where signal really means the electrical field or the voltage in a circuit or a current in a circuit somewhere. So distinguish between that on one hand, and on the other hand, the effective noise that we see on, let's say, demodulated information bits, right? It might result, for one thing, from thermal noise, but it might also be a consequence of interference sources and other things that can vary heavily over time and frequency. And then, as you suggested, I mean, interleaving is the standard way of breaking apart bursts of errors. So if you have a code word and many subsequent bits are affected by, for some reason, strong interference or disturbance, then, and your channel code isn't good at handling bursty disturbances like that, then the interleaver breaks them apart and kind of makes the effective noise uncorrelated over time. Yes.
So now we have also focused a lot on random channels models like Rayleigh fading or Rayleigh fading, and we also talked about the correlation that might exist, but whether we should exploit it or not when we build the algorithms is of course something that can be questioned. But why are we really modeling things randomly when it comes to the channel? Why not use the wave equation and solve it, or do ray tracing or make measurements? Is it one or the other?
No. I mean, solving the wave equations is just too complex, right? I mean, we don't have all the boundary conditions. You'd need like an exact geometric model for every little particle in the room here to figure out. And if you had that in principle and you had unbounded computational power, then certainly we could compute the impulse responses from between our, let's say, antennas. No question. So in principle that's possible, but it would require us to know again the exact layout and every little particle in here, which doesn't seem to be really feasible. So that's also really the reason why we use statistical models as an abstraction or as a proxy for ultimately solutions of the wave equation.
Yes, and I think also it's important to remember what model you need for a particular kind of evaluation, for example. I mean, it's one thing that we designed the algorithm for something, but if we are interested in sort of the statistical variations in communication performance, that someone is moving around in an environment that can be modeled by these random distributions, then yes, we should use a random distribution. If we want to understand the exact behavior of the wave propagation when you are at a different location in your room, then maybe we cannot still know everything, so we can solve the wave equation, but we can do ray tracing, we can do measurements, and those will be more accurate in that specific situation.
Certainly, I mean, one could use for performance evaluation just a set of measurements, right? And that would result in a very good prediction for what the system would work or function or perform like in that specific environment. But the real question is, how well does this generalize? Now, if you take your algorithm, your system, you move it somewhere else, will it still work as well as you concluded from your measurement sets?
Yeah, no, it's a bit with qualitative and quantitative analysis. Some things might work over large areas, but are not as precise for the local area, and the other way around. So what about all these path loss models that exist? 3GPP have there, you mentioned cost models earlier, and there is the Okumura-Hata models and things like this. Can we trust them?
Yeah, that's a good question. I guess the short answer is no, right? So path loss is a topic in itself. And I think the only uncontested path loss model that I think we could agree on is if we are in free space and we have line of sight, because then the amplitude of a spherical wave falls as 1 over r with distance. So the power density falls as 1 over r square. Now, for terrestrial radio, there are quite a few models for path loss. Many of them go back a long time, many decades into the past century. They capture to a varying degree of accuracy the main phenomena that we are exposed to in propagation. I mean, number one is the decay of amplitude with distance, obviously. Number two is ground reflection. Number three is like blocking by, could be trees and buildings and all sorts of things. And most of these models take the form of distance and then power or an exponent, so d2 minus alpha, where d is the distance and alpha is some exponent. And I like to say pick alpha equal to 4. It's probably quite reasonable. And then folks who have been doing modeling for modeling for like their whole life, they say, well, pick alpha equal to 3.81 or something, right? Well, the matter of fact is it doesn't make a huge difference in the end. And on top of that, it's also customary to add a log normal component, which is a random multiplicative effect, which is Gaussian distributed in the log domain. That, of course, is an entirely heuristic choice. And if you look at data, I mean, if you look at plots you can find in the standard textbooks in the field, in plenty, in fact, I mean, then, you'll see plots, right, where on the horizontal axis you have distance, on the vertical axis you have the path loss, and then these are measurements, and these plots like scatter plots, and they look like, you get really drunk, and then you close your eyes, and then you throw a dart at the wall, and then, you take these scatter plots and try to fit the regression line, right, in log scale, and then you'll get something like, well, maybe this exponent is about 4 or something, and then in order to explain how poor this fit actually is, then you'll say, well, let's add the random component, and log normal happens to be mathematically convenient, so we'll pick that. And I think it is probably as good as it can ever become, right? And the important thing here, though, is that model, in its simplicity, I think it's fair to say, I mean, this distance to minus alpha and then plus the log normal component, it does capture the fact that there is a lot of randomness in wireless, right? And that might be the important thing to actually capture. If we are, even setting up like simple simulation model for like the academic papers, right? So you have a cell, and then you have a tower, and then you have users, and you throw them out at random in the cell and so forth. And now let's model the like path loss spread. And what's really important there is to capture the randomness, that some users are going to be very close to the tower, might even have line of sight. Some of them are going to be far away. They might be shadowed by some objects and have extremely poor path loss. There is an enormous spread between the best and the worst condition and best and the worst path loss that anyone will ever see. And that is, I think, highly important to capture. I mean, this richness in the randomness. And the available path loss models do capture that. I mean, so Although it should be stressed, I think, that the log normal fading is an important component of that, right? I mean, this d2 minus alpha path loss might suggest that path loss is something exact, that it's an exact function of distance. No, it's not. And any analysis that relies on the suggestion that path loss is an exact relation with distance, I think is bound to give, very likely to give misleading conclusions. And the shadowing component is highly important to add in there in order to really model effect and the amount of randomness that we do have in reality.
Yeah, I was just reviewing a paper that essentially assumed such a model and then tried to use it for distance estimation, and they just applied the model, designed the algorithm that inverted the model, and then so I guess that's an example of what you shouldn't do when it comes to the models.
I mean, it might work, right, to the, let's say, not even first order, but if you just want to get like some estimate of the distance, if you have a very high signal strength, I think you can tell that you are close to the tower, right? But if you have a very poor signal strength, then you cannot say that you're far away. You can say that I'm either far away or I'm blocked by some object or I'm in the basement or something. So I wouldn't say that it's completely like useless. I think you can still make inference based on path loss measurements, but you got to be careful. I mean, not to over rely on simplistic models like this d2 minus alpha, and just we got to understand that there is a lot of randomness here, and it's so clear if you just look at the classical textbooks. I think I opened the other day, Ted Rappaport had this book on wireless communications, I think is the title, right? And there are all these scatter plots with path loss versus distance, and you really appreciate how much randomness there is in the physics behind this.
Yeah, and I think it's important to also mention that when those type of graphs are being generated, it isn't a drunk person who throws a dart. It is actually people who are selecting some propagation environment that's supposed to represent a particular type of world, and they go around, measure actual distances and measure powers and generate these points there. And then
absolutely
that's also why for different scenarios there are different path loss models. What happened to me recently was I had one paper where I used a path loss exponent of 3.76 and one with 3.67. And someone
you must have gotten vastly different results.
It was rather, I got an email from someone saying, "Oh, is this a typo?" And then I was really, oh, damn it, I have made an error here. But then I looked in the same 3DPP document that I have been referring to. You can find both of them in different tables for slightly different propagation environments. So I had been choosing them from there, but one can, of course, wonder if it should be a big difference. But going back to the shadow fading there, I also have the same interpretation as you, that this is something we just add because we see that this linear regression doesn't work, so we need to add some randomness to describe the data. Yet I think you can see in some textbooks, I was opening Goldsmith's textbook yesterday and saw that she was describing it a bit like, or trying to motivate why it is a good fit by saying, for every path it will be blocked by different objects, and they have a random thickness, and therefore in the log domain that thickness should become a linear thing, and then you have many paths, so therefore it should be Gaussian distributed. So try to motivate the Gaussianness using some arguments. And I was thinking, what is the chicken and the egg here? Is it that we should it be log normal, or is it just that it works?
Yeah, I don't know. I have to say I'd have to read that and analyze it to see what's really in there. But certainly one could probably find, physical justifications for Gaussianity in the log domain. It's very possible.
Yeah, no, I think there are always reasons why normal distributions are showing up sort of somewhat natural.
Yeah, but again, I mean, if there is one thing for listeners to remember from this conversation about path loss, I think it is that there's a lot of randomness in the path loss, and it stems from the shadowing, right? And the important thing is that we incorporate that randomness when we use these models for evaluation of performance.
So what about other models that might be exact? The superposition of user signals on the multiple access channel, is that an exact model?
Yeah, I think it is fair to say that it is. I mean, superposition principle on the MAC channel is an immediate result of the superposition principle for the wave equation, which in turn is a consequence of the linearity of the wave equation, which in now the wireless context means the set of Maxwell's equations. So I think there we can deliver a one-word answer, yes.
So that also means that other types of interfering sources are typically additive, right?
That's correct, yes. I think that is uncontested. I mean, that, these models for signal models that we like to write up, where you have your received signal equal to desired signal plus, and then you have a sum over interfering signals, then certainly the fact that we have additivity there is uncontested and results immediately from the wave equation. And also, of course, interfering signals, if they stem from systems that we have control over and where we design the waveforms, then the properties of those interfering signals will also be known exactly, right?
So are there things, in your opinion, that we as communication theorists are often ignoring, but is really important for future system design?
I think there are a number of things that many papers in comms and, let's say, comms in information theory also ignore. Then whether these are important for system design is really a little bit of a different question. But things that are often ignored, I think, are related to like actual antenna arrangements and how they relate to each other. Mutual coupling might be the most important effect there, which is typically almost always ignored. I mean, unless you look into literature on electromagnetics and antennas and so forth. But now, speaking of the comms and IT, maybe SP also literature. Coupling is a horribly important effect. I mean, if you have antennas that are closer than half a wavelength, then quickly coupling becomes the dominant physical phenomenon that you need to model. And along on the same train of thought here, there's also this notion of power, right? Which in the ITCOM SP papers we say that power is the norm square of the signal vector, or well, that's a fair approximation in many cases, but it can also be a rather poor approximation of reality, especially, I mean, in conditions where coupling effects are strong, right? So bottom line is that the actual radiated power from an antenna or from a group or any source for that matter, but let's say an array of antennas, isn't equal to what we call the power in the signal models. I mean, the X norm square, right? They simply aren't the same thing. And in some cases, they aren't even close to each other. If you have strong coupling effects, then the radiated power can be very different from just the sum of the squares of the voltages across the antennas or whatever, I mean, what we want our signal vector to represent. So that's another thing that we should be acutely aware of. And however, it's only really an issue if we put antennas closer to one another than half a wavelength. If the antennas are separated further apart, then, well, it's still not exactly true that the radiated power is equal to the norm square of our signal vector, but it's a good enough approximation that we can move on.
Yeah, when it comes to like an OFDM type of system, if you're measuring the power that you think you're assigned to every subcarrier and you add them up, then on the average you get more or less what you are supposed to radiate, but then you have these peak to average variations depending on how the subcarriers are actually adding up, if they add constructively or not, and that is also creating this instantaneous variations.
Yeah, certainly. I mean, that alludes to, I think, also what does power mean, right? Do we integrate over, well, So power in electromagnetics means that we have some source. That could be an antenna or an array of antennas, any radiating source, and then we enclose that source with a sphere or any closed surface for that matter, and then we integrate the Poynting vector over that surface. That's the radiated power. But I think what you're after here is that we might have a time and frequency varying source distribution, which in turn might be modeled as a random process. And then of course we got to decide on what do we mean by power. Is it the ensemble average of that randomness of the source, or is it some time average or something else, right? So certainly that's another thing to consider. Although this is a different point than the one that I attempted to make here, that coupling effects make the, let's say, information theoretic notion of power, the X norm square, actually different, and potentially in some cases very different from the physical radiated power.
What about nonlinearities and other imperfections in the electronics? I had the impression that it's hard to create good models for that. Is that your impression as well?
I think it depends on what you're after. I mean, look, if we have a power amplifier, then the closer we push it to saturation, it has a nonlinear transfer function to start with. I mean, nonlinear input-output relationship, and it saturates because it can only deliver so much power. So and this becomes more important the further we push it towards saturation. And now the question is, do we need a model for this nonlinearity? And what do we need this model for? And this model could be used for at least two rather different things, right? One thing is to examine, so now, given that we have these nonlinearities, what will the effect of that be on the radiate or on the amplified and eventually radiated signal or radiated wave? And for that purpose, we don't really need extremely accurate models. I mean, a simple polynomial model is quite good and does the job for us in terms of explaining out of band radiation effects and so forth. But on the other hand, if we want a model which is good enough so that we can design a pre-distortion algorithm, say that inverts the nonlinearity before we send the signal through the amplifier, then we would need a much more accurate model, and maybe a simple first or third order polynomial just isn't good enough, right? And you need some Volterra series or something with a lot of coefficients. So, yeah.
So if
was it your question?
Yeah. So if we are raising our eyes a bit now to other layers, when we are talking about millimeter wave communications or beyond, there's often the talk about blockage, which I suppose is when material is essentially absorbing everything, so you don't get any through. Can we get models for blockages and this type of things?
Yeah, so blocking, I mean, is partly modeled as a part of shadow fading that we talked about earlier, right? But I think if you go up into higher frequency bands like millimeter waves and so forth, then we'll very much see that blocking is almost like a binary effect. I mean, if you have line of sight, you might have 30 dB SNR, and then you put your hand in between, and then the SNR drops, I don't know how much, maybe orders of magnitude, tens of dB, right?
Yeah.
So you might rather be after something here like a model of like a good versus bad kind of model. I mean, you could think of like the simplest way of modeling good versus bad, I guess, is the Gilbert-Elliott, right? Which is a two-state Markov chain. You have two states, either you are good or you are bad, and then you jump in between of the two states with some probability. So for blocking, again, I mean, I think we got to distinguish between number one, on one hand, the model of the actual physics, what happens when you put an object in between. Well, the wave will be reflected and absorbed and so forth. And number two, what is the effect of the eventual path loss, and how does this effect vary with time? And to the extent that this effect is random, how do we appropriately model that? And for the latter, I think a simple Markov chain is probably probably most or all we need here. Link blocked or link not blocked, and then there is a possible transition in between the two states. So certainly.
Yeah, when we made an episode like a year ago about millimeter wave communications, I remember I was reading about measurement from NYU in the 60 gigahertz band, and I think the human body is blocking like 40 decibels or something like that in those bands. You really drop from a strong signal to nothing.
Oh yeah. Yeah, and the higher the carrier frequency is, the worse is this problem, right? Because propagation becomes more and more like distinct rays, and blocking becomes more and more of an important phenomenon.
So what about traffic models? What models are around there to say when does a user have data to transmit or receive, and when does it not?
Yeah, so there are of course large classes of models, and this goes, I think, beyond a little bit of things that I let's say know well enough that I can speak about from my heart. But in principle, I mean, you have a full spectrum there, right? From, on one hand, very simple arrival models, like packets arrive according to a Poisson process in continuous time, then, which is in a slotted time the same as, or becomes Bernoulli. So fundamentally they are like the same thing almost, or not from a mathematical perspective, but from operational meaning point of view. So they, on one hand, you have like simple models of that sort, and at the other end of the spectrum, you of course have like advanced models that describe how do humans function, and how do they generate data, and how do they browse the web, or or use applications, and how do these applications then generate data, right? I think what's important in the end here, so this is a little bit like with the path loss models, that, well, the exact model you use doesn't make a huge difference. What is important is that you account for the randomness in the traffic, and account for the fact that, well, you know, packets and bits will come in bursts, right? Sometimes it will be some silent or rather, say, sparsely populated segments in time, and then there'll be some bursts where everyone suddenly wants to send at the same time. And we gotta model the fact that this randomness is going to be there, and then the exact underlying model that we use for it might be less important, and in fact is not going to make a huge difference anyway in the end. It's a little bit like with a path loss, right? If you had 3.7 in your exponent, or you had 3.9, then yeah, you're gonna see like a tiny little shift of your curves, but it's not gonna change anything qualitatively, and it's not gonna affect anything that's important in your conclusions or your take-home points in your like papers. So I think that's really the message there, that we gotta figure out what are the first order effects that we see. And for traffic modeling, it is the like burstiness, and the fact that users don't have like data all the time. They have data that arrives randomly, sometimes a little, sometimes a lot, sometimes huge bursts, sometimes silent periods for a long time. We gotta account for that, and we're gonna in some way to the first order model that, preferably using as like a simple mathematical abstraction as possible, and then be aware that there is a lot of randomness, and we're going to account for that. We're going to build algorithms that are robust and function under these conditions of this randomness. And even when the models that we have, let's say, postulated or used aren't accurate or even nearly so, I think that's really the take-home point there.
I do think there is one aspect to there that might be of importance as well, that when we are having more and more other types of devices than human devices, or we have a large variety of different applications, it might be possible to sort of separate that some kind of devices generate traffic of one type and some of another type, and even if they are generating on the average the same amount of bits per hour, depending on if you have many short packages or a few long packages, you might want different types of protocols that have different overheads to set up the transmissions every time.
Yeah, Yeah, that's a great point. I mean, I think, well, machines and devices that we build and operate, they are easier to control than humans, right? And they are easier to predict. In fact, we can tell them how to behave. And if you tell them how to behave, then we know how they behave. So you could program your machine type device to be active according to some pattern that, you know, we have determined, right? And then that takes, of course, away the randomness. But if you have a human, then you can predict to some extent that, you know, I get up at 6:30 and I make my coffee, right? That's with probability very close to 1. But you can't predict like small variations in you sit and browse the web, exactly how you're gonna download the bits and and so forth on the application layer. So definitely, I think you're right. I mean, separating the two types of traffic and understanding that they are different in their characteristics, in the sense that the machines, in principle, we could make behave in a certain manner, whereas when humans are the end users, then yeah, we can predict to some extent, but we'll never be able to fully, and above all, we'll never be able, I think, to come up with a simple mathematical model that describes how a human behaves and acts when using an application in a wireless system.
So I have a last question for you now, and if it's like this, that particularly for path loss models and for these traffic models and things like this, that the way that we are generating the models is that we are making measurements and then we decide on, I would like to have a parameterized model of this kind, and then we try to fit the data to that one by finding these exponents and the standard deviation of the shadow fading and things like this. Do you think we should stop being the one selecting the models that we fit to the data, and that we should have instead machines that do machine learning and find the models for us? Is that the future?
Good question. I think to some extent we are heading a little bit that way, right? But first, what does it mean to have a machine learning algorithm develop a model? Well, what a machine learning algorithm can do at best is to find a mathematical description of what it has seen, right, of the training data, of the observations. Unfortunately, that mathematical description is extremely complicated in the sense that, I mean, it's essentially a nonlinear function, right? I mean, if you think of a neural network, for example, it is a nonlinear function with a lot of coefficients, millions of coefficients. And the real question then is that what is the added value of having a model then with millions of coefficients as opposed to 5 coefficients? Well, it might be valuable if the object is to predict performance in some very particular environment or set of circumstances. But returning to my previous point regarding the importance of just modeling, I mean, or acknowledging randomness, then it might also be that, well, what's truly important here is to have a model that to the first order captures the physical phenomena that we are exposed to, and that recognizes there is a lot of randomness there. That might be sufficient. So I'm just not sure how large the added value is. I mean, I'm certain that this can be done, no doubt. We could imagine a device that just, well, you just collect every channel impulse response you've ever seen, right? And you throw that into a neural network and you tell it to now, based on this, generate some artificial channel responses for me. And obviously that's doable, but the question is how large is the added value as compared to just using the Rayleigh model or something.
Yeah.
And there's also a risk that we lose the elegance and beauty of actual rigorous mathematics, right? Because that's something we should keep in mind, that some of them also we talked about here, they are very simple in their analytical form, and we can easily write them up with pen and paper, and we can convey, I think, at least some first order intuitive understanding for what they mean and how they work.
Yeah. No, I think one should remember that the reason that we have been using is sometimes very simple model, like it's a fine function of distance plus log normal when it comes to the path loss. It's not because we couldn't add 2 more terms that varied with the distance in a different way, but it was just because it fits rather well, and we don't want to overfit things completely. So from that perspective, it makes sense. And one final thing that I would like to bring up is also that we also should be careful with not using too simplistic models just because it's analytically more tractable to analyze certain things by hand. We should remember, is this model actually giving us the right answer, or should we use a slightly more complicated but not overly complicated model in order to get more accurate conclusions? Maybe use the tractable models for algorithmic design and the more detailed ones for analysis.
Yeah, I think if we were to summarize in like one punchline, that's not a bad one.
Do you have a final word?
Not really beyond that. I mean, possibly reiterating the point that I think I made several times, that there's a lot of randomness, right, in the phenomena that we are trying to model, especially propagation, but also like behavior of users and humans and so forth. And the very most important thing might be, in fact, that we capture that in the algorithms that we and models that we design, and then the exact way we capture it is really maybe less important in many cases. Yeah.
Great. So if you as a listener have your input, I think the best way of sharing that is by writing a comment to our YouTube video, and then we get the discussion started there as well. So we are monitoring that one and try to be involved in discussions. So with that, thank you for listening to yet another episode of Wireless Future. And thank you, Eric, for answering and sharing your thoughts around this topic.
Oh yeah, thank you, Emil.
And bye-bye.
Bye-bye.